All right, let's talk a little about the Doppler effect. Now, this is an artifact of this idea that that speed of a wave is determined by the type of wave and the material, and not the speed of the source and not the speed of the observer. So in order to fully understand this, you really need to know first about what determines the speed of a wave. And so that's actually learning target 157. If you haven't seen that one already, or if you're not sure on what determines the speed of a wave, you should watch that first. So click on the link that's on the screen right now and then come back to this one later on. I also want to point out that the Doppler effect is really, it involves motion of waves and motion of the thing making the waves and motion of the thing observing the waves, and I am drawing stationary pictures. So you won't be able to get a complete view of what's going on with the pictures that I'll have on this. I would encourage you to check out Dr. Daniel Russell's page. He's a professor at Pennsylvania State University. I'll put a link in the description to his site that has some really great animations of the Doppler effect and how this actually works. And I know he must have spent a great deal of time making these things really accurate and easy to understand. So definitely take a look over there as well. In fact, maybe take a look there before you finish this video. So first off, let's consider the situation where we have a stationary source and a stationary observer. And when I say source, I'm talking about, if it's sound waves, the thing that's making the sound. The observer is the thing that's detecting the sound. So maybe we have a police car here with its siren on, and here is a person listening to the police car. So in each of these diagrams, I'm going to be showing waves just as circles that move out here. They're going to look like ripples in a pond. And in fact, it's the same basic thing going on there. A different type of wave, and it's three-dimensional instead of two-dimensional, but same basic idea. So if we have our sound source producing waves, then it's going to make this sound, and we'll think of this as being like the high point on a wave. And that sound is traveling outward in all directions from that source. So all directions get this high point of the wave. And that is going to extend outward. And so over time, instead of being close to the source, it's going to extend out like this, and like this, and like this, and like this, like this, and so on like that. And so we see that each of these high points is, well, roughly equally spaced from each other. And so this observer is hearing these high points on this wave. So it'll go high point, low point, high point, low point. And high and low here we're talking about the pressure in the wave. But anyway, it works for all different types of waves. So some peak of the wave. And this observer is going to be detecting these. And so it gets a peak every so often. Every time one of these blue lines moves past the observer detects a peak. Now, how often it detects a peak will depend on how far apart these peaks are. So the observer is just going to sit there waiting for these peaks to come past it, waiting for these blue lines to come past it. So if they're really close together, then the observer hears a lot of peaks in just a short amount of time. That'd be like a high-pitched sound. If they're really spread apart, so more distance between peaks, then the observer detects a peak less frequently, less often. That'd be a low frequency or a low pitch sound. Now let's imagine that we have our source moving over to the right. Now what that does for us is these waves that are moving away, they move off at the same speed as they did originally. But the source doesn't stay in the same place making waves from that location. The source, let's say, is going to move over toward the observer. And so the source now is going to make a wave that's a little bit closer to the previous wave because the source itself is a little bit closer to the previous wave, in this direction anyway. If the source is moving over this way, then the wave that's over here is going to be a little bit farther away from the source and therefore a little farther away from the wave for the next cycle. The ones directly above it, they're basically not affected by this, so we wouldn't notice this this Doppler effect for an observer that's above our source. So if we have our source moving over to the right, what we'll find on this is that our waves are kind of scrunched together over on this side, but they're a little extra far apart over on the other side. And I made these waves really tiny, so I've got to draw a lot of these before they get to the observer. Okay, something like that. So this observer then is, again, just sitting there and waiting for these waves to come past it, waiting for these peaks to come past it. These waves don't have very much distance in between peaks, and so this observer detects a lot of peaks in rapid succession. It detects a high frequency of these peaks, or a high pitch of sound. So as this source is moving toward this observer, it's going to hear a higher frequency sound. If the observer were over on this side, where the waves are more spread out than they were to begin with, then over here, that observer would hear a lower frequency sound. So not just high frequency, but higher frequency than it would have heard if they were both still. And here, the observer would hear a lower frequency than if they were both still. All right, now let's say we have a stationary source again, putting out waves that look something like this. The other direction. Okay, so there's a set space all the way around from these waves, and now that our observer is going to not stay still, not just wait for the waves to come over the observer. Instead, the observer is moving either toward the source or away from the source. If the observer moves toward the source, they're going to encounter these waves more often. So there's a certain distance between these. They're moving over this way. If we move this direction, if our observer moves this direction, then the observer is going to encounter those peaks more often. There's less time that goes by between encountering those peaks. Effectively, the relative velocity is larger between the sound wave and between the observer here. So with a larger velocity but a constant distance between those, then the time between those waves is smaller, which means the frequency is larger. So the observer moving toward this source hears a higher pitch sound. If the observer were moving in this direction, now our relative velocity between observer and the waves would be lower. Or we might think of it as the observer is like trying to get away from the next wave, and so makes a little bit of progress, but eventually the wave overtakes him. So it takes a little bit longer for that next wave to catch up. This is just like if two people are running. If you're just going to stand, or say watching a race. If you're just going to stand and watch a race, then you'll have runners come by you every so often. If you run in the same direction that they're running, then the runners, if you're running slowly anyway, slower than the runners are, they'll still come by you. They'll still pass you by, but not as frequently. So it's going to be a little bit more time in between runners passing you by. So our period then is increasing. The time between peaks is increasing, which means our frequency decreases, so the observer that's moving in this direction hears a lower frequency wave.